Welcome to the Deep Dive. We're diving into foundations of statistical NLP today. It's all about the core ideas that make this field so fascinating. And don't worry, you don't need to be a math whiz to follow along. We're going to make it clear and understandable.
Absolutely. We're going to focus on the why behind these concepts. Why are they important? And how do they actually affect the way we interact with language in our digital world?
I'm really excited to have you here to help us break it all down. Your insights into language and data are exactly what we need.
I'm ready to jump in.
Perfect. So Chapter 1 gets right to the point. Why is a statistical approach to language so crucial? I mean, we all learned grammar rules in school. Shouldn't that be enough?
Well, those grammar rules are a good starting point. They give us a framework, but language is so much more fluid and unpredictable than just a set of rules. Think about it. We can understand sentences we've never heard before. We come up with new expressions all the time, and people still get what we mean.
That's true. It's like our brains are constantly doing these complex calculations without us even realizing it.
Exactly. And that's where the statistical approach comes in, by analyzing the patterns and frequencies of words and phrases in real language. The language we actually use, we can build models that capture this natural creativity and flexibility. It's amazing.
And that brings us to Zipf's law, which you explained earlier. The idea that a few words pop up constantly, while most words are pretty rare.
Right, like in The Adventures of Tom Sawyer. Just a handful of words like the, and a make up a huge chunk of the entire book. And this pattern isn't unique to Mark Twain. It's consistent across so many languages and genres.
So it's not just a quirk of one author's style. It's telling us something fundamental about language itself. Even though language seems infinitely varied on the surface, it's built on a surprisingly small set of very common words. And that has huge implications for how we process and store language, both in our brains and, of course, in computers.
Absolutely. And this connects to the idea of collocations, words that just naturally go together. It's like language has these preset combinations that pack in a lot of meaning.
Like international best practice. You wouldn't say global best practice, even though, those phrases seem like they could be interchangeable.
Exactly. Those subtle patterns add a layer of meaning that rule-based systems just often miss. They just can't quite grasp it.
Which brings up a big question. If language has all these statistical patterns, what does that tell us about how we learn and use language? Are we all just walking statistical models?
Whoa. Now that's a question worth pondering, and one that we'll definitely revisit as we go deeper into the book. Now, Chapter 2 lays out the mathematical foundation for statistical NLP. But don't worry, we're not going to get bogged down in all the complicated formulas.
Phew, I was a little worried about that.
Fair
I'll admit
point.
those equations can be a bit intimidating.
The important thing here is to grasp those basic concepts of probability. Things like probability spaces and conditional probability. Think of it this way. Every time you speak or write, you're making choices about which words to use. You base those choices on the context of what you're talking about and what you want to say.
So it's like language is this giant game of chance, but there are underlying rules that guide our choices.
You got it. And one of the most crucial tools we have in this game is Bayes' theorem. It's a way of updating our beliefs about something as we get more information.
It's like those aha moments when you suddenly see something in a new light because you've learned something new.
Exactly. Bayes' theorem is used everywhere in NLP, from spam filtering to machine translation. It helps these systems make smarter decisions based on the data they're processing.
That's incredible. And what about entropy? I remember seeing that term in the chapter too.
Ah, yes. Entropy is all about uncertainty. How much information a word or sentence actually carries. The more unpredictable something is, the higher its entropy.
So a sentence with a big plot twist would have higher entropy than, say, a totally predictable statement.
Exactly. Just like you'd be more surprised by a plot twist in a movie than a totally predictable ending. It's more unexpected.
Makes sense. Now, on to Chapter 3. We're heading into the world of linguistics. I always love dissecting sentences and figuring out how language works. But this chapter probably goes way beyond just diagramming sentences, right?
Oh, absolutely. It's like a crash course on those linguistic essentials. You need to really understand statistical NLP. We're going to touch on familiar concepts like parts of speech, but we'll also delve into deeper structures like phrases, clauses, and the relationships between words. Those dependencies are really important.
So it's like understanding the building blocks of language, how those blocks fit together to create meaning.
Exactly. And one of the big challenges for NLP is dealing with ambiguity. those tricky situations where a word can have multiple interpretations.
Like the classic bank example, right?
Yeah.
Could be a financial institution or the edge of a river.
Exactly. Humans can usually figure those out based on the context, but for computers, it's a whole different ballgame.
Which brings us to Chapter 4, the world of real language data. Corpora. It's like stepping into a giant digital library filled with texts from all over the place.
And let me tell you, it's not always pretty. Real-world language can be messy, full of slang, typos, and grammar that breaks all the rules.
But that's what makes it so interesting, right? It's like trying to solve a puzzle with pieces that don't always fit neatly together.
That's a great way to put it. And one of the first challenges is tokenization, figuring out what even counts as a word. It sounds simple, but trust me, it can get tricky when you start dealing with punctuation, hyphenated words, and multi-word expressions.
Like New York City, is that one word, two or three?
See, it's not always so straightforward. These are decisions that have to be made when you're processing text, and they can impact your results.
Then there's the level of detail. Do you analyze text at the word level or group things into larger chunks? What's the best approach?
It depends on what you're trying to achieve. Do you want to capture the nuances of individual words or focus on the broader meaning conveyed by phrases or sentences?
It's like deciding whether to zoom in on individual trees or look at the whole forest.
And this connects to something we all do every day, searching online. Search engines grapple with these same challenges. How do you find the information someone's looking for in a sea of data?
It's amazing how much complexity goes on behind the scenes of those simple search boxes. And speaking of interesting combinations, Chapter 5 takes us back to collocations, those words that just seem to go together more often than you'd expect.
Yes. We're going deeper now into how to find and analyze these collocations, going beyond simply counting how often they occur together to more advanced statistical tests.
I remember that example with strong and powerful. By analyzing their collocations, we see these subtle differences in meaning. Strong is often used for physical objects, while powerful tends to be paired with abstract concepts.
It shows how analyzing real language data can reveal nuances we might not even realize we're using. It's like language is whispering its secrets to us through the data.
But the book also cautions against relying solely on statistics. Human judgment is still important to understand those collocations in context.
Absolutely. Context is everything. A statistically strong word pair might not actually be a meaningful collocation in a certain context.
Now, Chapter 6 dives into a common problem. Sparse data. What happens when our models come across words they've never seen before?
That's where statistical inference comes to the rescue. We use the data we have to make educated guesses about those unseen events. We have to be a bit creative.
So it's like making an educated guess based on the evidence at hand.
Exactly. And one way to deal with this is through smoothing techniques. Essentially, you're smoothing out those probabilities to make sure even unseen events have a chance of occurring.
And how does that apply to things like predictive text, which often seems to magically know what we're going to type next?
Predictive text is a perfect example of how statistical NLP handles sparse data. These systems use Enneagram models, which predict the next word based on the words that came before. And they use those smoothing techniques to make sure they don't completely freak out when we type something new.
So even when we venture off the beaten path, linguistically speaking, these systems are working hard to make sense of what we're saying.
Precisely. And that's what makes statistical NLP so powerful. It's not just about rigid rules. It's about learning from data and adapting to how we actually use language, which is constantly changing.
Okay, on to Chapter 7, word sense disambiguation. I have a feeling those tricky words with multiple meanings are back to haunt us.
You bet. Like our old friend, bank. Are we talking about finances or a riverbank? This chapter is all about those techniques that figure out which meaning of a word is intended.
So we're giving computers the ability to read between the lines and understand the nuances of human language.
Exactly. And we have different approaches. Dictionaries and thesauri can provide clues, but we can also leverage the statistical properties of how words are used in context.
It's like how we as humans use the surrounding words to figure things out. If we see bank near money, deposit, or loan, we're pretty sure it's the financial kind.
And if we see bank near river, water, or flow, it's more likely to be the geographical kind.
It's amazing how effortlessly our brains do this. But for computers, it's a big computational challenge. How do they keep up with all those possible meanings and contexts?
That's where the magic of statistical NLP comes in. By analyzing massive amounts of text data, we build models that capture those patterns and probabilities. It helps computers make more informed decisions about word meaning.
Okay, Chapter 8, Lexical Acquisition. Can computers really learn new words and their meanings just from text?
That's the big question, isn't it? It gets to the core of what it means to truly understand language.
So what makes it so difficult to teach computers to learn new words?
One challenge is learning those selectional preferences. What kinds of things does a verb usually act on? For example, eat usually goes with food, not abstract concepts like freedom.
It's like understanding the grammar of meaning, how words relate to each other semantically.
Exactly. Another challenge is learning subcategorization frames, the different syntactic patterns a verb can take.
Like how give can be followed by a direct object. I gave her a book. Or both a direct and indirect object. I gave a book to her.
Right. And then there's semantic categorization, figuring out which words belong to the same category of meaning, even if they look or sound completely different.
Like grouping apple, banana, and orange together, even though they don't look or sound alike.
Exactly. And the exciting thing is that we're using statistical methods to tackle all these challenges. By analyzing huge amounts of text, we can infer these properties from how words are used in context.
So it's like computers are learning language in a similar way to how children do by observing patterns and making inferences.
I like that analogy, and it challenges the traditional view that we're born knowing a lot about language. It suggests that we learn a lot by simply observing how language is used around us.
What are some of the practical implications of this? How are we using lexical acquisition to improve NLP systems?
One application is expanding our dictionaries and lexicons. New words emerge, old words gain new meanings. Statistical methods help us stay up to date with those changes.
So it's like giving dictionaries a turbo boost, keeping them current with how language evolves.
Exactly. And this has implications for everything from machine translation to information retrieval, even to voice assistants. The better these systems understand the nuances of language, the better they can perform those tasks.
And of course, that leads to the ethical implications. What are the consequences of machines learning to understand language?
That's a crucial question we need to grapple with as these technologies become more and more powerful.
Okay, on to Chapter 9, Markov models. Those elegant frameworks for modeling sequential data.
And language is definitely sequential, right? Unfolding word by word, sentence by sentence.
So how do Markov models capture this flow of language?
They're based on this idea that the probability of the next word depends on the words that came before.
So like a chain reaction, each word influences the choice of the next word.
Exactly. And we have different types of Markov models. One type is the hidden Markov model, HMM, which is a workhorse in NLP. It's used for tasks like part of speech tagging and speech recognition.
Why are HMMs so useful for those tasks?
Well, take part of speech tagging. You're trying to figure out the grammatical category of each word, but you can't always do that just by looking at the word itself. You need to consider the context, the words surrounding it.
So an HMM can help us figure out if bank is a noun or a verb, depending on what words come before and after it.
Exactly. And in speech recognition, HMMs are used to model the sequence of sounds that make up a word, so the computer can understand what we're saying.
Wow, that's fascinating. So how do these models actually work? What are the key steps?
Well, first, you have to train the model. Feed it lots of data so it can learn the probabilities of different word sequences.
So it's like giving the model a crash course in language by showing it tons of examples.
Right. And then once the model's trained, you can use it to make predictions about new unseen data.
Like the model is putting its knowledge to the test.
Exactly. And Markov models have been super successful in so many NLP tasks. They really highlight the power of this statistical approach.
What about the limitations of Markov models? Are there situations where they might not be the best choice?
Well, they do make certain assumptions about the data. For example, the limited horizon assumption. It assumes the current state only depends on a fixed number of previous states.
Like the model has a limited memory of the past.
Exactly. And that can be a problem in language. The meaning of a word or phrase can sometimes depend on something that was said much earlier in the conversation.
Like those times when you have to remember the beginning of a story to understand the ending.
Exactly. And another limitation is they assume that the probabilities of transitions between states stay the same over time. But in language, those probabilities can shift depending on the context, the speaker, a whole bunch of factors.
It's like the rules of the game are constantly evolving.
You got it. But even with those limitations, Markov models have been incredibly useful. They're still a valuable tool for NLP.
Okay, Chapter 10. Time to put some of this knowledge into practice. Part of speech tagging? Here we come.
Yes. We're going to get into the nitty-gritty of labeling each word in a sentence with its grammatical category. Noun, verb, adjective, you name it.
I remember those charts from school, but we're not going to be doing this by hand, are we?
Definitely not. We'll explore how computers automatically assign those tags, comparing different approaches from those rule-based methods to statistical techniques, and even those powerful HMM taggers we just talked about.
So we're going to see those HMMs in action. I'm curious how they use those probabilities of word sequences to predict tags accurately.
You'll see how they take into account not just the current word, but also the surrounding words, using context to get those predictions right.
Like a detective putting together clues to solve a case. I bet there are different ways to assess how well these taggers are doing, too.
Absolutely. We'll dive into that as well, looking at the balance between accuracy and coverage. You want your tagger to be accurate, of course, but you also want it to be able to handle a wide range of words and sentences.
And how does this all relate to tools like grammar checkers or autocorrect? Those are lifesavers.
They rely heavily on part of speech tagging. By figuring out the grammatical roles of words, they can detect errors and offer suggestions.
So those squiggly red lines that tell us we messed up, those are powered by these statistical models working behind the scenes.
Exactly. And it shows how this seemingly technical task actually impacts those tools we use every day.
Okay, ready to move beyond those linear sequences of words.
Absolutely. Let's explore the hierarchical structure of language. It's fascinating.
Chapter 11, Probabilistic Context-Free Grammars, PCFGs. They can capture those relationships between phrases and clauses. It's what makes language so complex, yet so amazing.
It's like going from a flat map to a 3D model. We can see how words group together to form larger units of meaning.
And what makes PCFGs different from the context-free grammars we might remember from linguistics classes?
PCFGs bring in probability. They assign probabilities to each rule, so we can rank different interpretations and capture how likely different structures are.
It's like taking those abstract grammar rules and grounding them in reality, where some sentence structures are more common than others.
Precisely. And this lets us build parsers that can analyze sentences and create parse trees, those visual representations of the hierarchical structure.
Like seeing the skeleton of a sentence, revealing how the different parts connect.
And this structural analysis is key for so many NLP tasks. Machine translation, question answering, text summarization, you name it.
So by understanding the structure, we can better understand the meaning.
Exactly. But of course, training a PCFG can be tricky. Just counting how often rules appear might not be enough. We need more sophisticated techniques to get those probabilities right.
What are some of those techniques?
One powerful method is the inside-outside algorithm. It estimates probabilities based on a bunch of parsed sentences. It's a really elegant combination of statistical analysis and linguistic knowledge.
So it's like teaching the computer to learn from its mistakes and become a better parser over time.
You got it. But even with these fancy techniques, we have to acknowledge the limits of PCFGs. Can they truly capture the richness of human language using just syntactic information? I'm not sure.
That's a great question, and it leads perfectly into Chapter 12, which dives into the challenge of probabilistic parsing.
Right. We'll see how researchers are going beyond those purely syntactic models, incorporating more information about words and their meanings.
It's like adding more colors to our linguistic palette, right?
Yeah,
So we can create richer and more accurate representations of language.
I like that. And one key concept is lexicalization, bringing word-specific information into those parsing models.
So instead of just focusing on the word's grammatical category, we're considering its individual meaning and how it relates to the other words in the sentence.
Exactly. And this helps us tackle those ambiguities we talked about. For example, by looking at specific verbs and prepositions, we can often figure out how different phrases should be connected.
Like giving the parser a magnifying glass to see those fine-grained details.
And there are different approaches to lexicalized parsing, each with its own pros and cons.
It's like choosing the right tool for the job, depending on the complexity of the sentence and how much detail you need.
And then there's the question of evaluating how well these parsers are performing. We need to move beyond simply counting correctly parsed sentences, develop metrics that capture how similar the predicted parse is to what we consider the gold standard.
So it's not just about getting the right answer. It's about understanding how the parser got there. How closely does its process align with how humans would understand it.
Right. And this ties into how machine translation systems and voice assistants use parsing. They have to make sense of what we're saying and then translate that into action.
It's like parsing is the bridge between human language and what computers can understand.
Exactly. As we improve these parsing models, all these other applications benefit. It's really quite amazing.
Okay, ready for a linguistic trip around the world?
I'm ready for takeoff.
Chapter 13 opens the door to machine translation. This is where we see how statistical methods have completely transformed our ability to translate text from one language to another.
We've come a long way from those early rule-based systems that, well, let's just say they often produce some interesting results.
Remember those online translators that would spit out something that barely resembled human language? Hilarious, but not exactly helpful.
Those were the dark ages of machine translation. But with the rise of statistical machine translation, we've seen a huge improvement in the quality and fluency of translations.
So how did this revolution happen? What are the key ideas behind statistical machine translation?
One big idea is text alignment, finding those corresponding segments in parallel texts, even when the word order and sentence boundaries don't quite line up.
It's like solving a linguistic jigsaw puzzle, piecing together fragments from different languages.
Exactly. And there are different alignment techniques, from simple word matching to more complex models that take phrases or even whole sentences into account.
It's like going from a blurry image to a crystal clear picture. You can see those fine details of the alignment.
Once we have a good alignment, we can start building translation models. They learn those probabilities of translating words and phrases between languages.
It's like teaching a computer to speak a new language by showing it lots of examples of how words and phrases are translated.
Right. And one powerful model is the noisy channel model. It sees translation as a communication channel where the message gets a bit distorted by noise, those differences between the source and target languages.
So it's like trying to decipher a message that's been garbled in transmission.
Exactly. And the translation model's goal is to filter out that noise and recover the original message.
And how do we do that? How do we find the best translation out of all the possible options?
That's where decoding comes in. We use those statistical models to search through a huge number of possible translations and find the one that's most likely to be correct.
Like searching for a needle in a haystack, but using algorithms instead of a magnet.
And thanks to advances in statistical machine translation, those needles are getting easier and easier to find.
This has been an incredible journey so far. We've covered so much ground, from those fundamental probability concepts to the intricacies of machine translation.
And we're just getting started. There's so much more to explore.
We'll be back soon to dive into those next chapters and uncover even more amazing insights about the power of statistical NLP. Don't go anywhere.
Welcome back to our deep dive into foundations of statistical NLP.
We've covered a lot of ground, haven't we? From the statistical building blocks of language to working with real-world data. All those messy texts.
Right. It's amazing what we can do with all that data. Now, get ready to shift gears a bit. Chapter 14 takes us into the world of clustering. It's a powerful technique for grouping similar things together, even when we don't have neat categories defined beforehand.
So it's like letting the data tell us how it wants to be organized, rather than forcing it into categories we've already decided on.
Exactly. And there are two main flavors of clustering, hierarchical and non-hierarchical.
I remember those terms from my data mining days. Hierarchical clustering creates that tree-like structure, items grouped into increasingly specific clusters.
Right. Think of a family tree. The top level is living things, then it branches down to animals and plants. And you keep going down until you get to those very specific species.
And non-hierarchical clustering just creates groups without that tree structure.
Exactly. Imagine sorting your clothes into piles based on color. You don't worry about whether shirts and pants should be in separate categories. It's just about color.
Got it. So how does this all apply to language? What kinds of things are we clustering in NLP?
Well, we can cluster words based on their meaning, their part of speech, or even those roles they play in a sentence.
So we're grouping words that have something in common, but we might not know exactly what that commonality is before we start.
Exactly. And this is super helpful for tons of NLP tasks, building dictionaries and thesaurus, identifying topics in documents, even improving machine translation.
I can see how clustering would be useful in machine translation. If you can group together words with similar meanings across different languages, it seems like that would make translations more accurate.
Absolutely. And there are lots of different clustering algorithms out there, each with its own strengths and weaknesses.
It's like having a toolbox full of different tools. You have to choose the right tool for the job.
That's a good way to put it. The choice depends on things like how much data you have, what features you're using, and how detailed you want those clusters to be.
So there's no one-size-fits-all approach.
Nope. Clustering is a powerful technique, but you have to know its limitations and use it in the right way. Now let's move on to chapter 15, which takes us back to information retrieval, IR. We talked about this a bit in chapter 4, but now we're getting into the nitty-gritty of the web and its unique challenges for IR systems.
The web is like a giant, ever-growing library, isn't it? Billions of documents in all sorts of formats and languages.
And it's constantly changing. New content is being added all the time.
Right. So traditional IR techniques need some tweaking to handle this kind of environment. It's a whole different ballgame.
Absolutely. And what makes web search so different from searching a traditional database? Well, for one, the sheer amount of data is massive. Web search engines need to index billions of pages, and they have to do it quickly and efficiently.
That's a mind-boggling amount of data.
And then there's the variety of content. We're not just talking text anymore. Web pages have images, videos, audio, and who knows what else.
So it's not just about matching keywords anymore. It's about understanding all those different forms of content.
Exactly. And then there's the issue of spam and all that low-quality content out there. Search engines need to be able to figure out what's trustworthy and what's not.
It's like trying to find a needle in a haystack, but the haystack is full of fake needles and other distractions.
That's a great analogy, and that's where link analysis comes in.
Link analysis. Remind me what that is again?
It's about analyzing those hyperlinks between web pages.
Yeah.
We use them to figure out how important and authoritative a page is.
So it's kind of like judging a book by its cover. But the cover is the number and quality of links pointing to that page.
That's a good way to think about it. If a page is linked to by lots of other high-quality pages, it's more likely to be a good source of information.
Makes sense. It's like a web of trust. Pages vouching for each other.
Exactly. And one of the most famous link analysis algorithms is PageRank. It's what made Google so successful.
Oh, yeah. I've definitely heard of PageRank. It gives each page a score based on the links pointing to it, right?
Right. So the more popular a page is, the higher its PageRank score.
And then those pages with higher scores tend to show up higher in the search results.
Exactly. That's how Google decides what to show you when you search for something.
It's amazing how something as simple as analyzing links can have such a huge impact on how we find information.
It's really quite remarkable, and it highlights the power of statistical NLP to find order in what seems like chaos. Now, let's move on to chapter 16, text categorization. This sounds like it could be useful in so many different areas.
Absolutely. It's all about automatically sorting documents into those predefined categories. Think spam filtering, sentiment analysis, topic detection. The possibilities are endless.
Exactly. It's like teaching computers to organize information. And there are tons of different algorithms for doing this, from those simple rule-based ones to more advanced machine learning techniques.
So we're going to see some of those machine learning algorithms we discussed earlier in action.
You bet. And we'll also look at how to extract features from text to train these classifiers.
Features. What are those in this context?
Think of them as the clues the classifier uses to make decisions. For text, they could be things like how often certain words appear, whether specific keywords are present, or even how long the document is.
So we're giving the classifier a set of hints to help it figure out where a document belongs.
Precisely. And those features you choose can really impact how accurate your classifier is.
I can see how choosing the wrong features could lead to some pretty bad categorization.
Definitely. It's like trying to identify a bird just by its color. You're going to misclassify a lot of birds that happen to share the same color but are totally different species.
So you have to pick features that are really distinctive and tell you something about the categories you're interested in.
Exactly. And that often takes a mix of computational analysis and good old-fashioned human expertise. You need to understand the specific task and what you're trying to achieve.
And I'm sure there are ways to evaluate how well these classifiers are doing.
Of course. We'll get into metrics like precision, recall, and F-measure. They help us quantify how well the classifier is performing.
So it's not just about getting a yes or no answer. It's about